Alright, so in the previous lecture we saw the definition and description of the message passing decoder, sort of a philosophy of it in a loose way, how the beliefs are improved for the bits iteratively one after the other. Okay, but while I described it with, I described the decoder with notation and in a general way, it is always good to see a specific example and exactly what operations happen to make the ideas firm in our heads. Okay. So, that is what we are going to do in this little lecture. We will take a very small toy example. Okay. So, this parity check matrix that I show here is just a 4 by 8 parity check matrix. Nobody really uses this parity check matrix with message passing decoders and all that. In fact, you can implement easily optimal decoders for such codes. You do not need message passing and all that, but it is useful for illustration, just to show you what the operations are, what happens, what are the row operations, what are the column operations, etc. It is a nice illustration. Typically a much larger matrix is used, but actually extending it to larger matrix is not really difficult. It's just the basic idea is important. So, let us get started. So, we are going to focus on the MInsum decoder. We will not be doing log, tan, hyperbolic and all that, just MInsum. And how does that work? You have the received vector R1 to Rn entering your MInsum decoder, and you will put out an estimate for the code word C cap. Okay. Now, R enters this, there is an initialization which may involve some quantization, etc., whatever you may use, or it might go into the parity check matrix in some way. Okay. So, or the tan graph in some way, and then you have a row operation, column operation, and then iteration. Okay. So, this is the iteration step. Okay. You can do as many iterations as you want. Typically people do 10 iterations, 8 iterations, whatever, how many ever iterations you want. As you do more and more iterations, the performance will keep slowly and slowly improving. Okay. So, eventually you will see after some 8 or 10 iterations you may not see too much improvement in error rates. Okay. So, then you choose to stop. Okay. Finally, when you stop, you can make a final decision, and that will put out your C cap. Okay. So, this is sort of the block diagram of what happens. You iterate between row operation and column operation. Okay. So, this initialization and storage is sort of important. I will mention that as well. So, all these messages that are getting exchanged have to be stored somewhere, right, and you have to access them and do that. So, that is something I will illustrate as well. Okay. Alright. So, the storage matrix is what we will use, this notion of a sparse matrix which has the same dimensions as the parity check matrix. Okay. So, if you take for instance the new radio or the 5G standard rate half code, L will be a 22 by 46 times 48 sparse matrix. Okay. So, this is just an example, it could be of this size or it can be any other size, and the toy example is just 4 by 7. Okay. So, like I said, the real L matrix or the real parity check matrix will be very, very large, okay, but we are taking a toy example. Okay. So, the toy example, okay, so this I am sorry, I think I said it is 4 by 8, this parity check matrix is 4 by 7. Okay. So, the toy example is just a 4 by 7 matrix, a real code will be very, very large. Okay. The same thing is blown up, but remember it is sparse. Okay. The sparsity is quite important. Okay. Like I said, it has the same dimensions, it also, this L matrix also has the same sparsity structure as your parity check matrix. Whenever the parity check matrix is 0, this L will also be 0. Okay. So, it can be non-zero only when the h of ij is 1. Okay. So, the storage matrix is very important, you have to store it, and all your operations will be in place on the storage matrix. In place computation using this L. Okay. So, that is what we will do at least for the purpose of implementation and focusing our attention on understanding how the operations happen. Okay. Okay. So, here is the toy example. My parity check matrix had ones in the first row 1 1 0 1 0 1 1 1 1 like that. Okay. So, my storage matrix L will have possible non-zero values wherever there is 1 in the parity check matrix. If there is a 0 in the parity check matrix, this L will also be 0. Okay. So, keep that in mind, this is very important, L will become 0 otherwise. Okay. So, I have shown the same value x here, but just for convenience. So, I should have actually put x1, x2, x3, x4, okay, x5, x6, x7, x8. Okay. So, this value will keep changing. Okay. So, every value might be something else, it will keep changing with iterations. Just for convenience I have shown just one value. So, there are 17 values 17 non-zero values in this 2-dimensional matrix. Okay. So, every value, for instance x4 is in the first row 4th column, x17 is in the 4th row 7th column. Okay. So, you should be able to pull the values based on the row and column entries. Okay. So, this is my storage matrix. This storage matrix is quite important. We will use it in the illustration. You will see I will do in place computation. So, I will put values there, I will do some operations, I will replace the values, I will keep doing this iteratively. Okay. And as I do more and more iterations, the messages will be stored on the storage matrix. Okay. That is very important. Okay. So, what is the initialization step? Okay. So, you have the received value from the channel, you remember this, channel gave you this, there will be 7 received values because I am looking at a length 7 code in my toy example. Okay. I receive the values R1 through R7. Okay. Is that okay? So, what do I do here? You take R1 and store it in the non-zero positions of in the first column. Okay. Okay, all non-zero positions in the first column of L will have R1. Okay, that is the initialization step. Okay. So, all non-zero positions in the second column will have R2, all non-zero positions in the third column will have R3, all non-zero positions in the fourth column, and so on. Okay. So, you just imagine this, you can visualize that the received values are dropping on the columns, and wherever there are non-zero values they go and store themselves there. Okay. So, that is what happens. Okay. R1 gets stored on the first column, R2 on the second column, R3 on the third column likewise. Okay. So, this is just notation just to show how I am doing it. I believe I am using this n of j of I to denote the neighboring values and all that. It is not too crucial for us. Most important is to understand how these initialization happens. Hopefully, this is clear. Take the received values, every non-zero position in that particular column is occupied by that corresponding received value. Okay. Okay. So, the row operation is an in place computation using L. If you remember correctly, for each row I have to do a MInsum SPC SISO decoder. Okay. It involves finding the 2 minimum. Okay. You find the least absolute value among the non-zero values in that row, the next least absolute value, and then you set the magnitude of all values except the least value as min1. Okay, and set the magnitude of the least value as min2, and for the sign you first find the product of all the non-zero values in the row, and for every particular entry you either flip or not flip depending on the overall parity. If the overall parity is satisfied, you do not flip. If overall parity is not satisfied, you flip. Okay. So, this is the SISO MInsum SPC decoder. We have seen this before. Okay. So, let us see how we do this. Okay. So, here I have done the initialization. I have taken a sample value for R 0.2 minus 0.3, 1.2 minus 0.5, 0.8, 0.6 minus 1.1, and you can see in the initialization step the particular received value occupies all the non-zero positions in the L matrix. What are the non-zero positions in the L matrix? Once again, wherever you have ones in the parity check matrix, you will have the non-zero positions in the storage matrix L. Okay. So, you can see that is what has happened here, it is done. Okay. Hopefully, this is clear. So, now how do we do row operation? If you look at the first row, you have absolute value 0.2, 0.3, 1.2, 1.8. So, this is min 1, this is min 2. And what is the overall parity? Overall parity is minus 1. Okay. If you take the product of the signs, this is positive, first one is positive, negative, positive, positive. So, if you multiply the signs, you get minus 1, which means you have to flip the signs. Okay. So, in the least position, you put the next min 2, okay, but you put minus. Why? Because you have to flip the signs. So, you have 0.3 here, okay, you can see you have 0.3 here, minus 0.3 here, then everything else is 0.2 in absolute value, and you have flipped the signs. Okay. So, the original sign here was negative, so you made it positive. The original sign here was positive, so you made it negative here. Original sign was positive, you made it negative here, but you kept all the values 0.2. Okay. So, that is the row operation on row 1. Is that okay? As simple as that. Okay, just find the 2 least minimums and then do the substitution of the values and adjustment of the sign. Okay. So, now we can repeat this for every row. Okay. So, you do row 2, you see here this is min 1, this is min 2, okay, and the overall parity is plus 1, right, because minus 1 into plus 1 into minus 1 into plus 1, it became plus 1. Okay. So, now what do I do? The min 1 I replace with the min 2, okay, minus 0.5, everything else is 0.3 and the sign is retained as the original sign. Okay, wherever it is positive, it is positive. Okay. So, I do not want to illustrate any further than this, hopefully you can see in every row you do row operations like this. Okay. After you are done with the row operation, this is the matrix you will have. Okay. So, in every row you have the processed values for the entries there. Okay. How did we do the processing? We did MInsum SPC SISO decoding, this simple min 1 min 2 method. Okay. That is it. So, now the row operation is done. Now, we can do the column operation. For column operation, once again we will do in place computation using L. For each column we will find the sum of all the entries, okay, in the column plus the received value. Okay, remember the received value came from the channel, we have to do repetition code SISO decoding. We take the channel value, take all the values, add it all up. Okay, so, you will get sum j. Okay. Then the new entry will be the sum minus the old entry. Okay. So, this is the way in which we do the extrinsic computation for repetition code. Okay, once again what is this? This is repetition code SISO decoding. Okay. So, this is actually the total belief or LLR. Okay, I will call it belief. So, that is a better word here. Okay. So, this is the total belief, any decision you make will be based on the total belief, okay, at particular iteration. So, this is let me once again illustrate how this happens. Now, for the column operation in the first column, you look at the first column, the entries in the first column are minus 0.3, minus 0.3 and minus 0.6 and the value received from the channel is 0.2. So, the sum is going to be minus 1 here, is that correct? So, if you add up everything, you will get minus 1.2 plus 0.2 which is minus 1, is that okay? So, you see that, alright. And then what do we do? How do we find minus 0.7 here? So, you take minus 0.1 and then you subtract minus 0.3 from it, you get minus 0.7, is that okay? Minus 1 minus minus 0.3, okay, that became 0.7. So, what about here? Again the same thing, minus 1 minus minus 0.3, sum minus the old entry, okay, minus 1 minus minus 0.6. Okay, once again I will remind you, if add up all the entries of the column and the corresponding received value and the new entry is going to be the sum minus the old entry, okay, that is the extrinsic computation. So, now you repeat this for every column. Okay, what will you do in the second column? Okay, you add up everything, you get minus 0.4, okay, and then how do you replace the corresponding value? Minus 0.4 minus 0.2 is minus 0.6, minus 0.4 minus of minus 0.5 is plus 0.1. And then minus 0.4 minus 0.2 is minus 0.6, you add it up, that way you will be done with the column operation. So, now you can finish off all the operations and you get this. Okay. So, this is what is very important, this is the received value from channel. Okay. So, this is your belief if you do not do any iteration. Okay. So, what you got from the channel, you are not using anything in the code, that is your belief. Now, this is your updated belief after first iteration, the sum of everything is your updated belief after first iteration. So, this is the end of the first iteration when you have computed the total belief at the end of the first iteration and you have also computed the new L matrix. Now, this is the message from bit node to check node in the second iteration, okay, minus 0.7, minus 0.7, minus 0.4. You can do further processing, but this is your belief. Okay. So, if you notice this was 0.2, right. So, if you have to decide based on 0.2, you would have decided that the bit C cap is 0 here, but notice what happened to C cap here after your iteration, okay, it became minus 1. So, this is actually 1, is not it, right. So, here you have corrected something. Okay. So, in the next bit C cap is just 0. So, this is also 0 here. maybe I should write the C cap right below. Right. So, this was 0, 1, I am sorry, it should be also 1, 0, 1, 0, 0, 1. The C cap after the first iteration became 1, 1, 0, 1, 0, 0, 1. Okay. There was one bit which got flipped. Okay. This bit got flipped. Okay. You can see why that has happened. Okay. 0.2 became -1. Okay. So, because of your decoding this has happened. Okay. So, what you did here you can keep repeating. Okay. Whatever you did the first time you can repeat. Now, you have the L matrix, you can do row operations. You have the R also, right, the channel received value, okay, and you can repeat the column operation also. Okay. With once you have L, once you know how to keep updating it in row operation, column operation, you can repeat the same thing again and again. And every time you remember the sum is the total belief at the end of an iteration. Okay. You can make decisions based on the sum, you can threshold the sum to make decisions to get C cap. Okay. That is the important thing to remember. Okay. So, how do you make decision? If sum j is greater than 0, decision on bit j is 0. If it is less than 0, decision on bit j is 1. Okay. So, after the first iteration this was your sum and your decoded value is this. Okay. For more iterations you keep continuing with the new L. Okay. I illustrated this in the previous slide as well. Okay. So, here are observations. If you implement this, you will see if you do more iterations and if your parity check matrix is well designed, if it is a low density parity check matrix, you will get better performance with more and more iterations. Typically about 5 to 8 are enough for moderate block lengths. If you go to very large block lengths, you have to explore the entire parity check matrix more. So, you will need more and more iterations. Okay. Storage and efficient retrieval is the biggest challenge. Okay. The computations are not the biggest power consuming, area consuming implementation constraints for the LDPC decoder. The storing the entire L matrix and efficiently reading and writing into it parallelly is an important constraint, but today people have very good implementations working at very fast rates. Okay. So, that closes the example and a discussion on the decoder for LDPC codes. That is the end of this lecture. We will come back in the next lecture and look at how to do a slightly simpler implementation, what are the various modifications for this decoder. Okay. So, actually most people implement what is called a layered decoder in practice. So, we will discuss that specifically in the next lecture. Okay. Thank you.